Welcome, welcome, welcome. We are going to be studying the process of fusion today and actually doing a little comparison of nuclear fusion versus nuclear fission. This is actually the chemistry of the sun, so I'm pretty excited that we're going to be studying this. It's one of my more loving topics. It's near and dear to my heart a little bit. So if you will, we're going to start off as always, if we look at our agenda, with our bell ringer and vocab, and then we're going to move into our notes. That's day one. Day two, we're actually going to do a fusion lab, and we're going to have a little fun with science and comics. But that's day two. Today is day one. Let's get started. Here is your vocab for today. So you are going to be copying these down in your vocab section of your notebook. Just a reminder. It looks like this. Your vocab. Fantastic. Just go ahead and copy these down. Pause me. When we're ready, we're also going to do our bell ringer. For our bell ringer today, I would like you to write in the bell ringer section, make sure to put the date, and you are going to answer these questions. So we're doing a KWL chart. K stands for what do you want? What do you know? So what do you know about nuclear fusion? Do you know anything? What do you want to know? Please write down one thing you want to learn about how the sun makes energy. When you're done, unpause the video. Till then, we'll get started. So here's where we're going in your notebooks. Yours do not look as colorful as mine because you haven't finished them yet. But we're going to answer these questions, write these down, copy them, and talk a little bit more about fusion versus fission. So we're starting with fusion. Fusion is the joining of two or more things to create a single entity. In this case, we're talking about two cells, two hydrogen atoms, not cells, sorry. Thinking about two hydrogen atoms combining to become one helium atom. Nuclear fusion takes place when a small nuclei join to make a larger nuclei. Just as I was talking about, two hydrogen atoms are going to fuse to become one helium atom. The resulting process of this creates a helium atom, but it also creates a couple free neutrons and a ton of energy. And that's actually where the sun gets its energy from. So as always, if you need to, pause the video to copy these down. In stars, isotopes of hydrogen in high temperatures and under incredible pressure fuse to form helium. This is how many of the elements were initially made. So this doesn't, if you have just two hydrogen atoms sitting there in front of you, maybe, this isn't going to happen under normal Earth temperatures and pressure, right? You need the pressure of the sun and the heat of the sun to actually form, for this process to actually work. So you need high temperatures and high pressure for the two atoms to fuse and become helium. Fact checked, what are two conditions needed for fusion to occur? Just talked about it. It is pressure and heat. High pressure, high heat. Fusion usually occurs in atoms that are smaller than iron. So if you take a look at your periodic table, iron is Fe, and it is right here. So your atoms have to be smaller, which can mean that it's any of these, any of these, any of these, and any of these. And the smaller, the better. So fusion usually occurs in atoms that are smaller than iron. This is because iron is a dead end for fusion because nuclear reactions involving iron do not release energy. Okay, so the mass per nuclear particle is just too high to be able to, is just too low to be able to fuse the two elements together. Fusion reactors are being developed in order to harness the energy to produce electricity. We have not done this successfully in the world yet. We have, however, harnessed fission, which we'll talk about in a second. but not fusion yet. That's because we cannot replicate the high temperatures and high pressures needed to make the process work without spending too much energy, right? So it takes a lot of energy to create that high heat and that high pressure, that environment that's on the sun in Earth, and it's just not a economical solution just yet for creating energy. We haven't figured it out, but maybe one day we will. When this process happens, the reason why we get the sunlight that we do have is because an incredible amount of energy is released through this fusion reaction after the two atoms fuse. So, have we been successful in creating fusion chambers on Earth? Nope, not yet, but eventually we will. Or we have been successful, but it's not in a way yet that is economical or advantageous for creating energy. Moving on to nuclear fission. Nuclear fission occurs when atoms break down into smaller atoms. So with fission, we were taking two small atoms and combining them. With fusion, we were taking two small atoms and combining them. Fission, we're taking one large atom and splitting them in two. Both change the shape and the element, but they also both release a huge amount of energy. So the splitting or breaking down into particles is fission. So fission is splitting, fusion is fusing them together. Fission is splitting, fusion is putting them together, joining, okay? Remember those hand motions. Fission is splitting, fusion is fusing or joining those together. Again, this is splitting or breaking down into smaller particles. We already did that one. When an unstable atom is bombarded with neutrons, the nucleus breaks into smaller parts. So this one is here to tell you where we're going with this. So that's the arrow right there goes up to this little blue atom. So when an unstable atom is bombarded with neutrons, the nucleus breaks apart into smaller parts. So what this is saying is that the fission of two molecules, the fission, doesn't just happen naturally. We actually shoot little neutrons at it again and again and again until the atom eventually breaks apart. This usually occurs in atoms larger than iron. Remember, we saw that graph a couple slides ago. We'll go back to it in a second. So usually occurs in larger atoms larger than iron. Uranium is used in fission reactors here on Earth. So we have actually figured out how to create or recreate the process of fission here on Earth, and we do use it as an energy source. So we are taking these molecules and splitting them apart. We use uranium for this typically. It might actually be there. Nope. Okay, here's iron on your chart. So all of the ones that are larger, uranium is, can't find uranium on the chart. It's there somewhere. Okay. If we go back though, see, so if we're looking at this chart right here, again, this is where fusion occurs, right here. Fission though, you need to have larger atoms such as lead or uranium. Fusion can happen most likely in hydrogen, sometimes in helium, sometimes in carbon, and sometimes in oxygen. But it is most common in helium. So when you think fusion, I want you to think helium. When you think fission, I want you to think uranium. We like this process because it releases a lot of energy. We take this energy and we convert it to electricity. Space probes use fission as a heat source up in space because they do not have the atmosphere that traps the heat, meaning that it is very, very cold in space. Here's one example of a fission reactor, right? So if you stop and think for a second about the nuclear power plant, right? So it is nuclear. It's a nuclear power plant that is doing this fission process. If you think, we do use this, it is very common. It's especially common in Europe where they're trying to move away from the non-renewable resources like coal and natural gas. and switching to this fusion or fission is thought of as a cleaner energy, right? Has less waste, releases less carbon actually into the environment. But one thing that it is taking a toll on is that it has nuclear waste, right? And the possibility that the nuclear reactors could break down, we could have issues. Things like this happened in Chernobyl. So Chernobyl, I want to say Germany, but I'm not exactly sure. Chernobyl was a nuclear reactor, and back in, I'm feeling like it was the 80s, but I could be super wrong, could be the 90s. They actually had a meltdown in one of the reactors, and it didn't explode like an atomic bomb, but it did decimate the area and sense of radiation poisoning for those closest to it. So if you think of a nuclear reactor where it is, so the area around it was affected, and we had lots of radiation poisoning to organisms, so that could be humans, plants. It was through the water, and then it would spread through the water system, and it killed off, it had super deadly effects on those working in it, and within like mile radiuses of it. But even then, the radiation spread out into the environment, and kind of just the further away you got from the nuclear reactor, the less of effect, but there were still effects pretty far away. So it can be dangerous as far as malfunctions, but we do like to think of fission as one of the more cleaner energy sources. There's another example. This is 1 Mile Island, I think, in Pennsylvania. So they have nuclear reactors there. They're kind of separated, segregated in the middle of a river, but you could still, if one were to break down, you would still feel the effects in the surrounding areas. So neutrons are often emitted through fission, which can lead to a chain reaction. So I told you that in order for fission to occur, we are taking those heavy molecules and we are shooting neutrons at them until they break apart. But when they break apart, they not only release a large amount of energy, but they're actually releasing spare neutrons as well. And those neutrons can trigger other large molecules, and the process can keep going. So you could have a very large fission event. Okay, so that is the end of this lecture. Tomorrow we are going to be, or the next day, whatever day it is, we're going to be doing a lab in class. We're going to be trying to simulate the fusion of molecules, and we're also going to be learning about science in comics. It's one of my good friends owns the comic book shop here in town, Kessel Run, and we are going to try to incorporate different comics into our science lessons, because science is a common theme in comics. It's more along the lines of science fiction, but we can still look at it and kind of get an interest in what we're doing. So we're going to actually look at the Spider-Man villain from the 80s. His name is Fusion, or the Twin Terrors, and we're going to be learning about their story the next time I see you guys. Have a great day. Make sure to turn in your notes to Canvas to the correct spot. Make sure it's the correct file, please, please, please. You've started submitting good work. You're submitting, but sometimes I'm getting social studies work, and I need the correct assignment. Have a great day. Email me with questions. Goodbye.